Kinetic particle theory describes the states of matter, explains the differences in the properties of solids, liquids, and gases, explains the changes of state of matter. Why does a solid have a fixed shape? According to the kinetic particle theory, the particles of a solid are closely packed in an orderly manner, are held together by very strong forces of attraction, have enough kinetic energy to vibrate and rotate about their fixed positions only, cannot move about freely. Why does a solid have a fixed volume? A solid cannot be compressed since its particles are already very close to one another. Why does a liquid not have a fixed shape? In a liquid, there is more space between the particles. According to the kinetic particle theory, the particles of a liquid are arranged in a disorderly manner, have weaker forces of attraction than the particles of a solid, have more kinetic energy than particles of a solid, and are not held in fixed positions, move freely throughout the liquid. Why does a liquid have a fixed volume? The particles of a liquid are further away from one another than the particles of a solid. However, the liquid particles are still packed quite closely together. Why does a gas not have a fixed shape? The particles of a gas are spread far apart from one another, have weaker forces of attraction than the particles of a liquid, have more kinetic energy than the particles of a liquid, and are not held in fixed positions, can move about rapidly in any direction. Why does a gas not have a fixed volume? The particles of a gas have a lot more space between them compared to the particles of a liquid or a solid. The large space between the particles allows the gas to be easily compressed when pressure is applied. In other words, the particles of a gas can be forced to move closer together. Since a gas can be compressed, it has no fixed volume. Boiling properties. Occurs only at boiling point. Occurs throughout the liquid. Occurs rapidly. Evaporation. Occurs at temperatures below boiling point. Occurs only at the surface of the liquid. Occurs slowly. Melting. Heat is absorbed by the particles of the solid. The particles start to vibrate faster about their fixed positions. There is an increase in their kinetic energy. When the temperature is high enough, the vibrations of the particles become sufficient to overcome the forces of attraction between them. The particles begin to break away from their fixed positions. The particles are no longer in their fixed positions. The substance is now a liquid. The particles can move freely throughout the liquid. Melting process graph plotting. Solid heats up. The temperature of solid naphthalene increases until it reaches its melting point. Solid naphthalene starts to melt. Solid melts. During melting, the temperature of naphthalene does not rise even though heating continues. Heat taken in by the particles of the solid is used to overcome the forces of attraction holding the particles in fixed positions. A mixture of solid and liquid naphthalene exists at this stage. Liquid heats up. At the melting point, all the solid naphthalene has melted. The temperature of liquid naphthalene rises as heating continues. Freezing. Energy is given out by the particles of the liquid. The particles lose kinetic energy and begin to move more slowly. B. Decreasing temperature. Figure 1.11 Effect of cooling on the particles of a liquid time/min. All the particles have settled into fixed positions. The substance is now a solid. The particles can only vibrate about their fixed positions. Solid. When the temperature is low enough, the particles no longer have enough energy to move freely. The particles start to settle into fixed positions. We can use liquid naphthalene to study how temperature changes when a liquid freezes. When a graph of temperature against time is plotted, figure 1.12 is obtained. This graph is known as the cooling curve. A cooling curve shows how the temperature of a pure liquid changes as it is cooled to its freezing point, and beyond. Temperature/degree C 80 degrees Celsius, freezing point of naphthalene, P. PQ. Freezing process graph. Liquid cools. The temperature of naphthalene drops until it reaches its freezing point, point Q. At point Q, liquid naphthalene starts to freeze. Liquid freezes. During freezing, the temperature of naphthalene remains the same even though cooling continues. Heat is released as the particles of the liquid are attracted to each other to form a solid. This heat is given out to the surroundings. A mixture of solid and liquid naphthalene exists at this stage. Solid cools. At point R, all the liquid naphthalene has solidified. The temperature of solid naphthalene drops as cooling continues. Boiling. Heat is absorbed by the particles of the liquid. The particles start to move faster as the temperature rises. There is an increase in their kinetic energy. When the temperature is high enough, the particles have enough energy to overcome the forces of attraction holding them together. Boiling process graph. Liquid heats up. The temperature of tetrachloromethane increases until it reaches its boiling point, point X. At point X, liquid tetrachloromethane starts to boil. Liquid boils. During boiling, the temperature remains the same even though heating continues. Heat taken in by the particles of the liquid is used to overcome the forces of attraction between the particles. A mixture of liquid and gaseous tetrachloromethane exists at this stage. Gas heats up. At point Y, all the liquid has boiled. The temperature of gaseous tetrachloromethane rises as heating continues. Evaporation. Evaporation occurs because some particles have enough energy to escape as a gas from the surface of a liquid. The liquid particles left behind have less kinetic energy. The average kinetic energy of the liquid particles decreases and so the average temperature of the liquid decreases. At a higher temperature, the liquid particles have more energy. More particles have enough energy to escape as a gas from the surface of the liquid. Hence, evaporation occurs more quickly at a higher temperature. What is the effect of temperature on the volume of a gas? When a gas is heated, its temperature increases. The particles have more energy and the space between the particles increases. The volume of the gas thus increases. The gas particles have more energy and move further apart when heated. When pressure is applied to a GA, the particles move closer to one another. The volume of the gas decreases. How does the kinetic particle theory explain the effect of temperature on the volume of a gas? Gas particles are free to move. When a gas is heated, the particles have more kinetic energy. The particles collide with one another and with the wall of the container more often and at a greater force, move further apart from one another. The higher the temperature, the faster the particles move and the greater the volume of the gas. How does the kinetic particle theory explain the effect of pressure on the volume of a gas? The particles of a gas are spread far apart from one another. When we exert pressure on the gas by pushing in the piston of the container, the particles collide with one another and with the wall of the container more often, move closer together. If the gas particles are close enough, the forces of attraction between them become stronger and the gas will change into a liquid. Differences between element and compound. Element. An element contains only one type of atom. The smallest particle in an element is an atom. An element cannot be broken down into simpler substances. Compound. A compound contains two or more elements chemically combined in a fixed ratio. The smallest particle in a compound is a molecule or an ion. A compound can be broken down into elements or simpler compounds by thermal decomposition or electrolysis. Differences between mixture and compound. Mixture. The components of a mixture can be separated by physical processes such as magnetic separation, filtration, or distillation. The chemical properties of a mixture are the same as those of its components. No chemical reaction takes place when a mixture is formed. Usually there is little or no energy change. The components of a mixture can be mixed in any proportion. Compound. A compound can be broken down into its elements or into simpler compounds only by chemical processes, for example thermal decomposition or electrolysis. The physical and chemical properties of a compound are different from those of its constituent elements. A chemical reaction takes place when a compound is formed. Usually there is an energy change, e.g. the reactants get hot or cold. The elements in a compound are always combined in a fixed proportion. Properties of isotopes. Similarities. The same number of protons and electrons. Chemical reactions involve only the electrons and not the neutrons. Therefore, isotopes have similar chemical properties. Example: both chlorine-35 and chlorine-37 react with sodium to produce sodium chloride. Difference. Different numbers of neutrons. Physical properties are affected by mass. Isotopes have different masses and therefore different physical properties. Example: hydrogen-2 has a slightly higher boiling point and density than hydrogen-1. Covalent bonding properties. Low melting and boiling points. Why? Within each bromine molecule, the bromine atoms are held together by strong covalent bonds. However, between the bromine molecules, there are only weak intermolecular forces holding them together. Not much heat is needed to break these weak intermolecular forces. As a result, bromine has low melting and boiling points. It is volatile. Poor electrical conductivity. Why? Substances with simple molecular structures do not have free-moving ions and electrons to conduct electricity. Ionic bonding properties. High melting and boiling points. Why? In an ionic compound, the electrostatic attractions between the oppositely charged ions are strong. A large amount of heat is needed to overcome these strong attractive forces to melt the ionic compound. As a result, ionic compounds have high melting and boiling points. Due to their high melting and boiling points, ionic compounds have a low volatility. Good electrical conductivity when molten or in aqueous solution, but not in solid state. Why? When an ionic compound is molten or dissolved in water, aqueous, the ions are free to move. Therefore, the electrons are available to conduct an electric current. In the solid state, the ions cannot move freely as they are held in place in the lattice structure. What are the physical properties of ionic compounds? Ionic compounds are crystalline solids. Have high melting and boiling points, they are not volatile. Have good electrical conductivity when molten or in aqueous solution, but not in solid state. What are the physical properties of giant covalent substances? A giant covalent structure consists of a large number of atoms that are held together by strong covalent bonds. High melting and boiling points. Why? To melt or boil the substance, these strong bonds must be broken. This requires a large amount of energy. Due to their high melting and boiling points, substances with giant covalent structures are solids at room temperature. Do not conduct electricity, except graphite. Why? In giant covalent substances, except graphite, all the outer electrons of the atoms are used to form covalent bonds. Thus, there are no delocalized electrons that move through the structure to conduct electricity. Graphite. Graphite is another allotrope of carbon. It is soft, slippery, fairly unreactive, a good conductor of electricity, often used to make dry lubricants and inert electrodes. Can even be mixed with clay to make pencil lead. Its structure and physical properties are different from those of diamond. Graphite has a high melting point and a high boiling point. Why? Each carbon atom is covalently bonded to 3 other carbon atoms, which, in turn, are bonded to 3 more carbon atoms. This forms a continuous layer of hexagons. It is difficult to break these strong covalent bonds. Structure of graphite. Graphite is soft and slippery. Why? The layers of carbon atoms are held loosely by weak intermolecular forces of attraction. These layers of carbon atoms can slide over each other when a force is applied. Graphite conducts electricity. Why? Each carbon atom has one outer electron that is not used to form covalent bonds. These electrons can move freely along the layers from one carbon atom to the next. They are said to be delocalized. These free-moving electrons allow graphite to conduct electricity. What are the physical properties of metals? Good electrical conductivity. Why? While the atoms of a metal are tightly packed, the outer electrons of the atoms can break away easily from the atoms. Thus, the outer electrons are able to move freely within the metal lattice. These mobile electrons allow the metal to conduct electricity. The greater the number of delocalized electrons, the better the electrical conductivity of the metal. Malleable and ductile. This means that metals can be hammered into different shapes, malleable, and drawn into wires without breaking, ductile. Why? Before a force is applied, the metal ions form an orderly and rigid arrangement. When a force is applied to a metal, the layers of metal atoms can slide over each other through the sea of delocalized electrons. The metallic bonding is not disrupted.